Hi everyone. Today I will be talking about cosmology and the expansion of the universe. So I know the professor have already covered a bit yesterday on yesterday's lecture. So she have shown you some results of the Friedmann equations and like some important like how the density of each component vary the expansion of the universe. But so today I will focus on more details of the derivation and interpretation of these equations. Today's problem session will the most part will be focusing on derivation. So just let me know if I'm going too fast or too slow at any time. Okay, so the first part, I will derive the Friedmann equation, and then the second part, I will derive the continuity equation. So these two are the most important equations in the Friedmann cosmological model. Okay, so let's first talk about the expanding universe. Okay, so let's consider a uniformly expanding sphere and treat the sphere as our expanding universe. Uniformly expanding sphere. Okay, so let's say this is our universe and it is expanding. So let's say the radius of this sphere is r of t. So the radius should vary with t because it is expanding, right? So the radius will grow larger and larger. And then let's say the initial density of this sphere is rho I, the initial rho. Okay, so as I said, the density would grow larger and larger. So we can write r of t equals some scale factor, a of t, times the r. Okay, so the little r is it's like the initial radius is very, very small. And a of t is like the factor that it grows with time. Okay, and also the density also vary with time, right? Because as you grow, the radius grows larger, the density will be lower down. So the density can be written as the initial density and divided by a cubed. Because like a of t is the scale factor for a linear scale, and now we're considering the whole volume, so that's a factor of a cubed, right? All right, so with these two equations, we can estimate the mass of this expanding sphere. So we know the mass can be written as 4/3 pi r squared times the density, right? So rho of t times r cubed. Okay, so since we know that r of t is small a times r, so this can be reduced to r of t, I missed the pi. So pi rho of t, and r of t can be written as a cubed times r cubed, right? Okay, so why are we calculating the mass? Because with this mass, we can determine the acceleration of a particle, like with a very easy Newtonian physics point of view. So let's say there's a particle here at the boundary of this expanding sphere. So the acceleration this particle would experience is r double dot, right? And that can be like from Newtonian physics, that is just negative gm over r squared. And then with the m, we just derive. We can plug in that m into this equation and write. So r squared is just a squared times r squared, small r squared. And then the mass can be written as pi, and then a g here. And then, okay, so here is a rho of t term, right? Rho of t times a cube of t. So from the density equation, we know this is just rho I, right? We have rho I equal rho of t times a cube. Okay, so we can simplify this to rho I, and then the last term left is r cubed. Okay, so we can cancel out r and left with only 1. And then, okay, this can be simplified to minus 4 pi g over 3 times rho I times r over a squared, right? Okay, and this, so this whole thing is double dot of large R, double dot of big R, right? And we know big R is a times small r, so double dot of R would be the double dot of a times small r, right? Because small r is a constant. Okay, so by comparing this expression with the one we just derived, so we can ignore the small r now, and then we will get the expression of double dot a, right? Okay, so we can write a double dot is 4 pi g rho I over 3a squared. And this is, okay, so the rho I can be written as I just mentioned, it is rho of t a cube, rho of t a cube, yep. And then, so it can cancel out with the a squared in the denominator, right? So that would just left us with 1a in the numerator. Okay, so rho of t, a of t. Okay, so if we multiply this equation by 2 times a dot, we will get 2a dot a double dot equals negative 8 pi g. 8 pi g over 3, and there's a dot term, so rho of t, a of t times a dot, right? Okay, so for this term, 2 times a dot times a double dot, this is basically just the time derivative of a dot squared, right? And then this term here, a of t, a times a dot, we can write it as a cubed times a dot over a squared, right? So this is just like we can cancel out the a squared terms, and we're writing it. We're writing in this form because this term, a dot over a squared, is just the time derivative minus the time derivative of 1 over a. Okay, so by rewriting this, we have the time derivative derivative of A dot squared equal, so the two negative signs will cancel out. So that's 8 pi g over 3 times rho of t a cube times the time derivative of 1 over a. Okay, so basically this term is just rho I, so it's a constant. So we can take it out. It doesn't influence the time derivative. So we can then write this as a dot square or a pi g over 3 times rho I and times 1 over a, right? And then if we convert again, like we convert back the rho I to rho of t times a cubed, then we can cancel out the a terms and get a pi g over 3 rho of t times a squared, right? So this would lead us to the Friedmann equation, which is a dot over a squared equals a pi g over 3 times rho of t. Okay, so this is the Friedmann equation, which you will also be using this in your homework. And okay, Friedmann. I'm not sure if it's. I think it's Friedmann equation. All right. So this term, so the Friedmann equation, the first term here, a dot over a is defined as the Hubble constant, a dot over a, and why is that? Because so we know the simple form of the Hubble's law is the velocity equals h naught times the distance, right? So there's a linear relation between the receding velocity and the distance. So by considering the particle at the boundary of the expanding universe, we can calculate the proper distance of that particle. So it should be very simple. The proper distance is basically just a of t times dr. So we can write the proper distance with time as a of t and integrating from 0 to r. And that is just a of t times r. Okay, so if we take the time derivative of this equation, we will get dp, the proper distance, the time derivative of proper distance equal a dot times r. And we can write a dot into a dot over a times a, right? And then the r here. So now we can identify this as just the proper distance, right? So that, and also the time derivative of proper distance is basically just the velocity, right? So now it should be very easy to identify this term as the Hubble parameter. So basically you can see this equation here is in the same form as the Hubble's law. So the a dot over a term is just like the Hubble constant, but varying with time. So we call it the Hubble parameter. Okay, So I should also mention that the Friedmann equation we are writing here is for the flat spacetime. So we're deriving this in the Newtonian physics point of view, but so if we derive this with general relativity, there should be an additional term of minus kc squared over a squared here, where the k is 0 if this is a flat space-time. So just in case if you are curious about how it is derived in general relativity, so I can give you some general picture of how this is derived. So basically, the Friedmann equation is derived directly from the Einstein field equation. So it's okay if you haven't learned general relativity before, but I just wanted to give you a picture if you have already learned it, or maybe it would be helpful when you are learning it in the future. So the Einstein field equation is the Riemann curvature tensor, and it would be equal to 8 pi g times this is the stress energy tensor. And so basically these two terms, the Riemann curvature tensor is defined through the Christoffel symbols, right? So if you have learned that before, through the Christoffel symbol and its derivative. So let's say delta here. Okay, and the Christoffel symbol is basically also defined as it is composed of the metric tensor, the spacetime metric, and the derivative of spacetime metric. So with the Christoffel symbol, we can obtain the we can trace it back to the spacetime metric or the derivative of spacetime metric. Okay, and we can see that here is also a term of spacetime metric. So if you look at the Friedmann equation, it is basically relating the a dot over a term with the density distribution, with the density variation, right? And the density term is here in the stress energy tensor. Okay, and then if you calculate the Riemann curvature tensor, then you will get many terms of the spacetime metric. The spacetime metric is basically related with the a dot and with the scale factor term, because so for example, if we're considering if it's a flat spacetime, then we will have a line element of ds squared equal minus dt squared plus the scale factor times the x squared. So here x is the three-dimensional spatial coordinates. Okay, so there is a squared term in the spacetime metric. So that's why we can derive the Friedmann equation directly from this Einstein field equation. Okay. So, this is just a short note. Okay, so any questions so far on the Friedmann equations? Okay, so if there's no equation, no more question, I will move on to derive the continuity equation, which is also another important equation in Friedmann cosmology. So, okay, so this part we're going to derive the continuity equation. Okay, so in general relativity, this equation is basically derived from the conservation of the stress energy tensor, which can be written as the covariant derivative of the stress energy tensor is 0. But you can just think this as this. So this is just a conservation of energy and momentum. So, okay, so without using general relativity, we can we can also derive this using the first law of thermodynamics, which we know is also the energy conservation condition, right? So instead of using GR, we will use the first law of thermodynamics. So this is written as dq equal dE plus P dV, and that will be equal to 0, right? So this is just the energy conservation. So we know that to use this equation, the condition to use this equation should be that so the situation should be, the system should be under adiabatic condition, right? And the reason why we can assume this because we are considering a homogeneous and uniformly expanding sphere. So we can use this so that it would be adiabatic due to homogeneity. All right, so with this very simple equation, we can derive that. Okay, so let's first do the time derivative. We will get dE dt equal negative P dV dt, right? And the dV here, the volume here, we can replace it with the scale factor to the third. So, and in our case, the energy here is simply just like, it's in the form of mc squared. So it's rho times a cubed and c squared. Okay. So this term is just density times volume. So that's kind of the mass term. Okay, and then let's write this out. So let's write out the energy. So it's now rho c squared times a cubed dt equals negative p dA cubed dt. Okay, and then let's write out the time derivative, which is we can take c squared out, right? So that's c squared, and then to do the time derivative for both terms, that is rho dot a cubed plus rho times dA cubed dt. Okay, so next we can see that there's a dA cubed dt term here, right? And there's also a term here. So let's move these terms to the same side. Okay, so the left-hand side will be left only with rho dot a cubed c squared, and then the right-hand side would be there's a minus term, p plus rho, p plus rho c squared. There's a c squared term. n times dA cubed dt. Okay, so now we are very close to the continuity equation. So now we can write rho dot equal minus p plus rho c squared divided by a cubed c squared, and then dA cubed dt is 3a squared times a dot, right? All right, so now we can cancel out the a terms and left with only one in the denominator. And that will give us minus 3 a dot over a rho plus p over c squared. Okay, so this is the continuity equation. Okay, I'll write this again. So the continuity equation is rho dot equal 3. This is the Hubble parameter times rho plus p over c squared. Okay, so basically, this term is the pressure, right, from our thermodynamic equation, and these are the density distributions, and this is the scale factor of the expanding universe. Okay, so any questions for the derivation of for the derivation part? Okay, if not, so basically this equation can tell us, so as shown, I think you've heard this from yesterday's lecture, that this equation can tell us how the density variation of each component in our universe will determine the expansion of our universe, like whether the expansion is accelerating, decelerating, or does it expand forever, or is it so something like that. So basically, we can relate the pressure term in this equation. Like the pressure will depend on what kind of component we are considering. So basically, we're considering we can consider three kinds of matter. So the first one is the general matter, which is, it's the cold non-relativistic particles, like cold dust or something so it's just general matter. And then we can consider radiation from photons, and then also the vacuum energy, right? So we know these are the main components of our universe. So so different components will have different terms of pressure. So the first one, if we're considering general matter, or more specifically, it's called non-relativistic particles. So for general matters, we will have a pressure of approximately the rho c squared, where this c is the sound speed, and we know that since it is non-relativistic, this rho c sound speed should be much smaller than the sound speed than the speed of light. Sorry, So this tells us that the pressure divided by c squared is basically just 0, right? And okay, so I should mention that basically all the components we are considering, we can write them as the pressure. We can write the pressure as a constant, like omega times rho c squared. So then we can derive a general form by just varying this constant of omega here. Okay, so by comparing with general matters, we can see that the omega is simply just 0, right? And then, okay, so I should probably talk about the general form first, and then go into each component. So let me move this down a bit. Okay, so if we have a general term of P equal omega times rho c squared, then if we plug in P equal omega rho c squared into the continuity equation, we would get rho dot plus 3h and 1 plus omega rho equals 0. So this is the general expression of continuity equation. And then with this differential equation, we can we can easily verify that the solution of rho is a constant, rho naught, it is an initial density times a to the minus 3 times 1 plus omega. Okay, so you can also easily verify this by just plugging it in this solution into that differential equation. So, okay, yeah, so now we can basically just plug in the different omega constant from different components into this solution and see how that component vary the expansion. Okay, so I just mentioned that for general non-relativistic matter, omega is 0, right? So that means if we plug in omega equals 0, we will just get the density of matter is rho naught times a to the minus 3rd, right? And then the second part, if we consider photons. So for photons, the radiation pressure is basically 1/3 rho c squared. So that means omega is 1/3. And then by plugging in this into this form, this density, we will get the radiation term. The radiation should be proportional to a to the minus 4th, right? Okay, and then last, for vacuum energy, so for vacuum energy, the pressure is just approximately rho c squared. And then, so that means omega is 1. And if we plug in omega equal 1 into that density equation, we will get, sorry, for vacuum energy, it's minus rho c squared. So the dark energy, like the pressure of the dark energy that accelerate the universe will always have a negative term. Okay, so in this case, omega is -1. And if we plug in -1 into that density equation, the exponent will cancel out. So we have the density of vacuum energy is just a constant, right? Okay, so the density of these three matters can tell us that how the variation of them can vary the how the variation of these components, like by plotting. So for in standard cosmological model, using the Friedmann model, so we basically have omega matter of about 0.3 and omega vacuum energy of about 0.7. So this is determined from observations, right? So we observe the type 1a supernovae and then find the density ratio to the critical density of each component, and then we get this value. So this should be consistent with observations, and then the radiation, the component of radiation, should be very small. So it's around the order of 10 to the -4th or -5th, which is very small comparing to the other two components. So with these parameters and also the Hubble parameter, Hubble constant, so we now know it's about 70 kilometers per second megaparsec. Yeah, so with all these values, we can see how the density of each component vary with the scale factor, which also vary with time, right? The scale factor. Okay, so we can make a plot of log density and divided by the critical density. So the critical density is defined as 3h h naught squared over 8 pi g. So yeah, so we have the critical energy just because we're using omega here, and omega is defined as the density divided by the critical density. And so I believe you have seen this plot in the lecture already. So since we have the vacuum energy equal constant, so we'll get so this is for the vacuum energy, and then the photons is okay. So let's first deal with the matters. So the matters is decaying with a to the -3rd, right? So it should be something like this. And then the photons is decaying with a to the -4th, right? So there should be a steeper slope in this plot for radiation. So let's say this is for radiation, okay? So now with this plot, we can see that there is a specific time where the dark energy have the same amount of matter. And there's also another time that the matter have the same amount as radiation, right? Okay, so we can determine the time at which, like at these two specific time. So we know there are 3 regions. So so in the recent universe, our universe is dominated by the dark energy. But in a earlier time, the universe is actually dominated by matter. And then in even more earlier time, the universe is dominated by radiation. Okay, so, and we know that A of t, the scale factor, is basically just related, it's related to the redshift as 1 over 1 plus z, right? So, so you can try this when you, like after this session, you can try to determine the time at which like those components has the same densities, and you will get A equal about 0.77 if you use these constants. And that if you convert that to redshift, you will get z equal 0.3, about 0.3. So it is until z equal 0.3 that our universe start to be dominated by the dark energy. So it is like very, very recently. But okay, and you can also derive the time at which the radiation and matter have similar densities, and you will get a very small value. So you'll get this value is about 2 times 10 to the 4th. And if you convert to redshift, I remember it's something like, or something around between 3,000 to 4,000. So yeah, so this means that like this is at the very, very early stage of the universe, right? So yeah, so at very, very, very early time, the universe is dominated by radiation and then matters, and then until recently, it's dominated by dark energy. Okay. Okay, so just in case if you still don't know how to calculate the A or the Z at this time, I'll give you some hints. So for example, if you want to calculate A m lambda, then so you simply just set the density of lambda. So at that point, the density of dark energy should be equal to rho m over A cube, right? So you're setting the density of dark energy equal to the density of matter, and then you can get this equals to rho m over rho lambda, and then you can also divide this by the critical density, which we will use, and then you can get this value. Okay. Yeah, so this is all I want to cover in today's problem session. So any questions?
Yeah, I have a question. I don't get how you can find the time with the Z.
How you can find time with Z? You mean you know how to find A, but you don't know how A is converted into Z? Is that a question?
Yeah, I mean, A, it's equal to 1 plus C power minus 1.
Yeah.
But after that, there is something we can use or do to convert the Z into actual time.
Right. So
Yeah,
by converting Z into actual time, you can like use the look back time, right? So basically you just integrate the, for example, if you want to know the actual time from Z equals 0 to Z equal 2, for example, then you can integrate this with the Z, right? So that term here, you can derive this. And I guess this is a part of the homework problem, right?
Yeah, it is.
Yeah. So
okay, so this is how we can convert Z into actual time.
Yes, exactly.
Okay, thank you.
So